So welcome everybody on this Sunday to the Indian Institute of Astrophysics for a popular talk by Professor Bharat Ratra. Very happy you're here. We know that it might rain in the evening, so we're happy you could have braved it and came here. Of course, if it rains very tense, we just hang on for a much longer question answer session than otherwise. Very happy to have Professor Bharat Ratra here. And to introduce him, I request Professor Prav who's the chair of the Group 23 or Theoretical Astrophysics group at the Bharat.
Welcome everybody. It's nice to see very big crowd on Sunday. We are very fortunate to have Professor Bharat Ratra with us today. He has made very significant contributions to the area of cosmology. And it is my pleasure to introduce him to you today. So right now, Professor Ratra is a distinguished professor of physics at Kansas State University. So he works in the area of cosmology and astroparticle physics, and he particularly studies the structure and evolution of the universe. So he is particularly interested in developing models for the large-scale matter and radiation distributions in the universe and testing those models using cosmological data, observational data. And he is quite well known for his pioneering work in the 1988. He basically proposed a model that the dark energy, he's going to talk to us about dark energy. So he proposed a model that the dark energy is a dynamical model, first model, along with Professor Jim Peebles, who won the Nobel Prize a few years ago. And this is also quite exciting. You might have all heard of the dark energy spectroscopic instrument results, which came out a few days ago. And it said that possibly dark energy is dynamic. Professor Ratra has mentored several graduate students, postdoctoral fellows, and visiting faculty members. He's very distinguished. He has got several grants and recognition for his work and awards. So he's a fellow of the American Physical Society. He's a fellow of the American Association for the Advancement of Science, the American Astronomical Society. He has been awarded the Olin Pettefish Award in Basic Sciences in 2017. In 2020, he received the Kansas Science Communication Initiative Communication Award. And he was also awarded the American Physical Society's Julius Edgar Lilienfeld Prize in this year, 2025. So Professor Ratra is also very keen on communicating science and outreach activities. So he is a founding member of the North Central Kansas Astronomical Society and the Kansas State University Center for the Understanding of Origins. And he is actively involved in several outreach efforts. And it is also interesting that he started out his journey as a master's student in IIT Delhi. And from there, he moved to get his doctorate in physics from Stanford University. And he was a postdoctoral fellow at Princeton University and the MIT. So today he will tell us all about dark energy, the accelerated expansion of the universe in the current year.
Very kind of introduction. Thank you. It's a pleasure to be here. So before I start, I just wanted to point out this website. It's connected to those cards you have, and it's got some really nice videos that clearly explain global warming. It's probably a good thing to be talking about because it's going to become a huge problem. So I am a cosmologist, and that means I'm interested in things, how they're distributed in space on very, very large length scales, like both electromagnetic radiation, other kinds of radiation and matter, and how these distributions change in time or how they evolve. And it's a really exciting time to be doing cosmology because all of you have seen pictures from James Webb and other telescopes. And the data that they're bringing in is extremely good now compared to what we had in the past, excuse me. So these data are reinforcing two very striking results. So one of the results is that when you look at the energy budget that's driving the expansion now, that we only understand 5% of that, and that's the atoms and molecules that we're all familiar with. The remaining 95% is split into two parts called dark energy and dark matter. And all we're seeing is the gravitational effects of dark energy and dark matter. We don't know what they are. So 95% of the stuff in the universe is still unknown. So there's a lot to do in cosmology. The other result that's getting reinforced is that these observations are suggesting that either quantum mechanics or special relativity and general relativity or both are incomplete. And if that holds up with new measurements, then it's going to be very profound because quantum mechanics and relativity have been the foundations for all of physics for almost a century and a quarter now. So let's move on. And this is near where I live in Kansas. It's prairie, it's tallgrass prairie, and it's a really interesting place to go hiking. So I have questions for you. How many of you have gone hiking at least 10 kilometers in your life? Can you put your hands up if you've gone that far? What about 100 kilometers in your life, integrated, cumulative? What about 1,000 kilometers in your life? What about 10,000 kilometers? Okay, so there's an upper limit that you can directly access reality at through your senses. I mean, if you're a little bit older and have a lot of spare time, maybe it's 1,000 or 10,000 kilometers. So the next thing I want you to do is for those of you who have hair, to reach up and grab a single strand of your hair and feel it. And I mean, is that about the thinnest thing your fingers are sensitive to? It's somewhere around there, right? So if you have thick hair, it's about 100 microns in diameter. If you have thin hair, it's 10 microns in diameter. So I have a number of length scales here. The units are in meters. So a typical human is 1.5 meters or so. And this is in powers of 10 notation. So 10 to the 5, another 100,000, another 100,000. So it covers a lot and goes down to very small scales also. So if you are old and patient and like hiking, maybe you get out to 10 to the 6, 10 to the 7 meters or so. And if you have very sensitive fingers, maybe you get down to 10 to the -4 meters. But those are the only length scales you can directly access through your senses. And you become experts. I mean, you didn't even really know this, but when you started walking, you became an expert in Newtonian physics. You wouldn't survive if you didn't understand Newtonian physics in a very fundamental way. And Newtonian physics are the rules that govern what's happening over here. And they don't work that accurately when you get out to very large scales where special relativity, general relativity become more important. And they don't work on very small scales because quantum mechanics is more important. And they're both in some sense corrections to Newtonian physics, but those corrections become very significant on large and small scales. So everybody is an expert in Newtonian physics, whether they understand that fact or not. Because you can't walk, you can't move around without being an expert. And so all your intuition about the real world is built up here. And you can't build up intuition about what's happening here the same way. You can't touch those things. I mean, here, if you take an apple and drop it and you have a pendulum and a measuring stick, you can figure out the inverse square law of gravity. But you can't figure out general relativity like that. You can't figure out how a star works. So what you have to do with a star, I mean, you can't go walk to a star. You have to take a telescope, you collect that light, you store it, pass it through a CCD and store it in your computer. And then you build a mathematical model, you put some gases there, atoms and molecules, and heat it up and let it rotate and turn on the gravitational field. And then you try to produce a spectrum and you compare it to the spectrum you've stored in your computer, and if they agree, and you improve your model mathematically and you improve the data you're getting, and then you try to refine the model you have. And you also can't touch atoms, you can't touch electrons or protons and neutrons. So the way you develop intuition over here and here is fundamentally different from the way you develop it over here. And so maybe that's why people find quantum mechanics and relativity somewhat unintuitive in that sense. And they're very important because mobile phones won't work without quantum mechanics, and you can't use GPS without general relativity. It won't work properly. So I want to spend a little bit of time walking out this way to larger and larger length scales. And I'm not going to talk much about here, but if you're interested, there's a bunch of videos, and I saw some chalk here. There's a very famous one called The Powers of 10, and it's from the 1970s, and it's made by two architects. They call the Eames brothers. And you could probably find that on your favorite search engine. And the American Museum of Natural History has an updated one of this. It's also called The Powers of 10, I think. They're worth looking at, and they give you a nice idea of the length scales. But I'm just going to look at the larger length scales. So we'll start out with a typical human length scale. Instead of using meters, I'm going to use a new length unit, and it's going to be the Einstein. So an Einstein is roughly 2 meters. And so I want to compare an Einstein to this small planet here. And so we're going to do an experiment. We're going to drill a tunnel from the North Pole to the South Pole and build a strong base here. And then go and get 6.5 million Einsteins and put one on the base, and the next on his shoulders, the next on his shoulders, and so on. And then you'll cover the diameter of the Earth, and 6 is roughly equivalent to 10. So that's going to be 10 million Einsteins, so a factor of 10 to the 7, going from a human scale to the scale of this small planet. We can step out further and look at the sun, the nearest star to us, and think about the same sort of thing, drilling a tunnel from here to here. And to cover it, you'd have to put 100 Earths, one on top of the other, so it's a factor of 100 bigger than the Earth. And if you want to do that in terms of Einsteins, you'd need 700 million Einsteins. So it's a factor of 700 million bigger than a human scale. And we can step out even further and look at the Earth's orbit around the sun. This is not drawn to scale, but if you look at distance, it's 1.5 into 10 to the 11 meters. And you know that the sun is approximately 1/100th of that distance in diameter. So if you lie down 100 suns in a row from the surface of the sun, it'll reach to the Earth's orbit around the sun. So it's another factor of 100 in terms of the ratio between the size of the sun and the size of the Earth's orbit. Or if you want to do it in terms of Earths, the factor of 10 to the 4, you'd have to lay down 10 to the 4 Earths from the sun's to the Earth's orbit point. And you can do it in Einsteins, and then it's 75 billion Einsteins. So it's a pretty big factor. So it's very, very inconvenient using the meter as the length unit when you're looking at the solar system. And there are 2 other units that people use. So one's the astronomical unit, and that's abbreviated the AU. And that's just the average of the Earth's orbit around the sun. If you average it out over the course of the year, the elliptical part, you can approximate by an average circle. And that's the radius, that 1 AU is the radius of that circle. Another really useful unit to use for measuring lengths is to use the fact that light in vacuum has perfected cruise control. So you have cruise control in your car, so if you just set it at that speed, then you can continue going at that speed. And light travels at exactly the same speed, no matter what direction it's going in a vacuum. And that's a really large speed. It's 3 times 10 to the 8 meters per second. Or if you want to convert that to feet per second, it's about 1 billion feet a second, because a meter is 3 1/3 feet. And that's a useful number to think about, because a foot is about this much, and light covers this distance in 1 billionth of a second. It's very, very fast. So if you divide this distance by the speed of light, you get approximately 500 seconds. And so that's telling you light takes 500 seconds to come from the sun to the Earth. So when you're looking at the sun, and if you look at the sun, you need to use protective equipment, otherwise you're going to damage your retinas. So when you're looking at the sun, you see it 500 seconds in the past, you don't see it in the present. And you never, ever see anything in the present. If you look at the person next to you, who's probably 2 feet away, you're seeing that person 2 nanoseconds in the past. But your brain doesn't care about nanoseconds, and so it automatically gives you this intuition that you're seeing somebody in the present, but you're never ever seeing anybody in the present. And that becomes much more significant when you get out to large distances, because those distances, it takes light a long time to cover, and so you see it very far back in the past. So then we can step out from the solar system to the nearest star to the solar system, which is Proxima Centauri. And that's another factor of 10 to the 5. Or in terms of light travel time, light from Proxima Centauri takes about 4 years to reach us when we're looking at it. So in terms of AUs, Proxima Centauri is about 200,000 AUs away. And so you're starting to get many powers of 10 when you use AUs as the length unit when you're looking at collections of stars. And so it's not that useful a length unit for collections of stars. Instead, what astronomers use is another unit, which is called the parsec, which itself is an abbreviation. It stands for parallax of an arcsecond. And that is usually abbreviated to PC. And so this is a cartoon explanation of what a parsec is. You take your astronomer, give her a telescope, and send her so far away that this huge length unit here, linear unit 1 AU, subtends a really tiny angle at her, an angle of 1 arcsecond. So if you go around a whole circle, there's 360 degrees in it. And each of those degrees you can break up into 60 arc minutes, and each arc minute you can break up into 60 arc seconds. So if you multiply 360 by 60 by 60, you get roughly 200,000. So there's roughly 200,000 arc seconds around the whole circle. And so arc second is a very tiny angle. So this observer has to be very far away. So when this angle is 1 arc second and that linear length is 1 AU, she's 1 parsec away. And for us, it might be useful to remember that light takes 3¼ years or so to travel 1 parsec. So it's easy to convert to light travel time if you have the distance in parsecs. So just to make this a little bit more concrete, the furthest humans have ever been is to the moon, and maybe a little bit further because of the orbits of the rockets they use. But the moon is about 1 1/3 seconds away in light travel time. And Pluto, maybe you can take Pluto's orbit to give you roughly the size of the solar system. That's 40 AUs. It's 40 times the distance between the Earth and the Sun. Or in light travel time, it's 6 hours compared to the 500 seconds between the Earth and the Sun. And the furthest anything has gone are the 2 Voyager missions. They were launched in 1977. And these are numbers from 2017, the 40th anniversary. So at that point, Voyager had gone 140 AUs, 3.5 times the distance from the Sun to Pluto. And in light travel time, it's 19 1/3 hours. But in terms of parsecs, it's less than 1,000th of a parsec. And the nearest star is roughly a parsec away, a little more than a parsec. It's about a parsec and a third. So if you're using Voyager technology, it's going to take tens of thousands of years for something like that to get to a star, the next star. So they're really far apart. So we can step out even further, and this is our Milky Way. It's a collection of 150 billion to 200 billion stars. A typical star has a mass that's maybe half the mass of the sun, and it's spread out. This is a really nice image, and it's much nicer if you can look at it on the computer. It's the European Southern Observatory Milky Way, or ESO Milky Way. You can zoom in on it, you can find it on the ESO webpage, and you can find it on other pages, and it's well worth looking at. So you can see how the technology has changed. Like 50, 60 years ago, this was what we had for the Milky Way, and it's much better now. And this is probably the easiest way to discuss it. So it's like a frisbee, it's a disc, and we're looking at it edge on, and there's a bulge in the center. And so if you look at it from the top of the bottom, you'll see a sort of circular disc. and you'll see the spiral arms where the bright baby stars are. And the size here is 50 kiloparsecs, so kilo is 1,000, so it's 50,000 parsecs diameter of the disk. And I told you 1 parsec is roughly 3¼ light years. So if you want to convert this to light travel time, you multiply 50,000 by 3¼ and you get about 160,000 years. So if something was traveling at the speed of light and we can't travel at the speed of light, you have to be massless, and you started it out here and pointed it that way, it would take 160,000 years to cross this. And just remember that the distance between the sun and Proxima Centauri is 4 years, and the distance between us and the sun is 500 seconds. So this is a huge disk here. We're 1/3 of the way out. And there's a bulge in the center of the Milky Way. And right at the center is the galactic nucleus, and that's where our black hole lives. It's got a mass of about 4 million times the mass of the sun. And that's pretty heavy, but this is actually a pretty underweight black hole compared to black holes at the centers of galaxies. A lot of them are 1 billion times as heavy as the sun. So we can see the structure here, and it's spread out. And that's immediately telling us something very, very interesting, because we know stars are very heavy, and from Newton's law of gravity, they're going to pull each other together. And so the fact that the disk is still spread out is telling us that it hasn't collapsed down to a point, and there's got to be some other source of energy over there, because without that source of energy, these stars would all fall in. And what's happening is that the stars are rotating in the disk, and they have energy of motion or kinetic energy. And because they're rotating, they also have a conserved quantity called angular momentum. And the same sort of thing happens with the moon's orbit around the Earth, because the Earth's gravity is trying to pull the moon down, but the moon has kinetic energy, and so it stays in orbit. And so we know that the stars are rotating. We can actually measure the rotation, but we know, because this is spread out, that there's something going on. And because this is a bulge, there's something going on over here also, because if it was left to gravity, gravity would pull it all together and crunch it down to a point as much as possible. And so what's happening here is that the stars are also moving, but they're moving randomly. They're not rotating systematically like they are in the disk. So this galaxy, our Milky Way, is about 160,000 years across in light travel time. And it's actually sitting in the center of a much, much bigger object, which is called the halo. That's probably 10 times as big, maybe 1.5 million light years across. And that halo is where there's a lot of mass and there's a lot of dark matter there. And that gives you a very, very strong gravitational potential well. And our galaxy, the shiny part, is sitting at the center of that potential well. And in the halo, there is collections of stars called globular clusters, hundreds of thousands to maybe a few 100,000 stars. And they held together by their own gravity, and they orbit around the center of the Milky Way, and all in 3 dimensions. They come out of the plane of the board also. So if you haven't seen these objects through a telescope, they're well worth seeing, and I'm sure there's opportunities here, and you can go observing and see these things and even see parts of the Milky Way. So how many of you have seen the Milky Way? Okay, that's great. And those of you who haven't might want to see it. Pretty spectacular. So this is another spiral galaxy. This is our nearest neighbor galaxy. It's Andromeda. It's also a disk galaxy, and you can see the spiral arms, and you can see the central bulge. It's a little bit bigger. It's 60 kiloparsecs in diameter. And if you turn that into light travel time, it's about 200,000 years to cross this at the speed of light. And it's about 750 kiloparsecs from us. And so in terms of light travel time, it's about 2.5 million years. So if you look at Andromeda, how many of you have seen Andromeda? Okay, just a few. Okay, so those who haven't should go try to look at it. When you look at Andromeda, that light that's hitting your retina now left either a star or some hot gas 2.5 million years ago, and it traveled in a straight line and came and hit your retina after traveling for 2.5 million years. And 2.5 million years is an interesting time for human evolution on Earth. Perhaps the most famous fossil is Lucy. She lived in what's Ethiopia now, about 3.18 million years ago. And apparently she climbed a tree to sleep and stay away from predators and fell out of that tree 3.18 million years ago. And that's approximately 700,000 years before the light you see from Andromeda hit your retina now, before it left Andromeda. So that's kind of the time scale on Earth then. So we can move on to bigger objects. So galaxies are collections of hundreds of billions of stars. They're very, very massive. And so if they come next to another galaxy, they're going to pull together. And some of these get close enough to form clusters, collections of galaxies. You can have tens or dozens or even thousands of these galaxies together. And this is the center of the Virgo cluster. It's a nearby cluster and it's a rich cluster. And there's probably 150, 1,500 or so galaxies that you can see here in the center. So every spot of light is a galaxy. So even these little guys are galaxies with 100 billion or 200 billion stars. These big guys are in the foreground because Virgo is spread out. And so some of the galaxies are closer to us, and so they appear bigger because they're nearer us. And they're in orbit and moving around, and the scale here is a few million. M is mega, and that's 10 to the 6 million parsecs. So in light travel time, maybe 7, 8 million years to cross this at the speed of light. So this is a huge object, but it's a very, very tiny object on the scale of the universe. So this is a picture, so I'll show you where this picture was taken. So we're here orbiting the sun, and they pointed the telescope up to this region and looked at the cap over here of some width on the sky, and it's the North Galactic cap. And it was taken at the Lick Observatory, which is in the hills outside of San Jose in the San Francisco Bay Area. And then they developed that, and they didn't have laser scanners, they didn't have computers. So what they did is they took a little microscope, an eyepiece microscope, and strapped it onto the edges of the glass plate. And they had a little screw drive, and they moved it along in lines along that plate, and used paper and pencil, and figured out the positions on the sky of 400,000 galaxies by looking through this little microscope and using paper and pencil. So there's some students here, I guess, and you sometimes get upset with your homework. So this might be a useful thing to think about when you get upset with your homework. So the scale here at this distance from us is about 300 million parsecs. On light travel time, 1 billion years. So if you travel at the speed of light, it would take you 1 billion years to cross this. And you can compare that to the 500 seconds between the Earth and the Sun, which is a huge distance on human scales. And this is much, much, much bigger. So you can see clusters here. That's the Coma cluster. It's got maybe 6,000 or 7,000 galaxies, each having 100 billion, 200 billion stars. And so it's a huge, huge, huge object, but it's just a few pixels here. And you can see many, many, many other clusters. Some of these are closer by, and some of them are further away. And if you look carefully, you can also see darker regions. These are the voids, that's the name given to them. And you can also see one-dimensional filamentary-like structures, and these are called filaments. So the easy way to understand this is to think about the bubbles. If you're lying in a bubble bath in your tub, the galaxies avoid the center of the bubbles. That's why they're called voids, because there's no bright galaxies there. The dimmer galaxies are more uniformly distributed, but the bright galaxies seem to be on the surface of the bubbles. And where you have two bubbles coming together, you have two surfaces intersecting, so you have an enhancement in the number of bright galaxies. And when you look at that in the sky in projection, it appears to be a one-dimensional structure that's shining more brightly. And those are the filaments. And these filaments, where you have a lot of galaxies, bubbles coming together, you can see the filaments kind of draining into the clusters of galaxies. So when you have a lot of bubbles coming together, you have filaments, and the filaments kind of end up in the clusters of galaxies. So this is a very, very non-uniform distribution, and there's a technical name for it. It's said to be anisotropic. So if you have an isotropic distribution, that's an easier place to start with. So this is a distribution, so you kind of are standing at one point and you're looking around you in all directions, and above you and below you and in front of you and behind you. And if the things you see look the same, no matter what direction you look in, you're seeing an isotropic distribution. And you can immediately tell this room is very anisotropic, because you look to your right, you don't see the same person that you see above you, or you don't see a person above you that's the same as the person on the right. It's very anisotropic. And if you go up 100 kilometers above Bengaluru and look to the south, you might see, or even the east or the west, you might see the Indian Ocean. And you look to the north, you don't see an ocean there. And if you're high up enough, you'll see the mountains. And you can do the same thing in the solar system. You look in one direction, you'll see a big star that we call the sun. You look in any other direction, you don't see an equally big star nearby. And you can do this in the Milky Way. You look towards the center of the galaxy, you see many more stars. And you look this way, you see many fewer stars. So it's anisotropic, it's not isotropic. And neither of these is isotropic. This is also not isotropic. So maybe that's not surprising, because everything is anisotropic. And what happens when you go out another factor of 20 in length scale, the distribution changes. And this is a picture of the afterglow of the Big Bang. It was taken by the European Space Agency satellite called Planck. And it's called the cosmic microwave background radiation anisotropy. So it's cosmic because it's a really large scale, it's the cosmological effect. And it's microwave because that's the part of the spectrum that we're seeing here. And these are very, very long wavelength light, electromagnetic radiation, very long compared to what you see with your eyes. And if you use this at home to cook with the microwave oven, that's the same radiation. And it's background because it's around us everywhere. It's radiation, it's electromagnetic radiation, and it's anisotropy because it's bumpy. So what was done was they took this Planck satellite and they put a microwave detector on it with a spectrograph, so something like a diffraction grating. And they looked at the whole sky, so they would rotate the detector and look everywhere above and below, and to the right and to the left and in front and behind. So they're looking at the interior surface of the sky. And so you can kind of think you're inside the center of a beach ball. And I sliced that beach ball from the North Pole to the South Pole and opened it out, spread it out, and placed it here. So if you want to go back and reconstruct it, you just stand in the center and pull it around you. And this is what you'll see on the interior of that beach ball. So they had this spectrograph in there, and so they could get the color of the light that they were seeing, whether it's whether it's longer wavelength or shorter wavelength, higher frequency or lower frequency. And from a little bit of physics, once you know the color of the light, you can tell the temperature. So they're basically measuring the temperature. And so what they have here are red hot spots and blue cold spots. And this is not the usual convention in physics, but in this map, the red spots are hotter and the blue spots are colder. And so they measure the temperature of the light that's coming to us from the surface of this beach ball, and they measure the temperature as it hit the detector. So the temperature, the first thing maybe you're interested in is the average temperature across the whole sky, so you can average this out. And it's roughly 3 Kelvin. So Kelvin is the science or engineering scale for temperature. It's not the C scale that you use every day here. But if you do measure the temperature of this room, it'll be about 300 Kelvin. So this room is very, very hot compared to the temperature of the microwave background, which is 3 Kelvin. At 0 Kelvin, all classical motion stops. The only motion you can have is the Heisenberg uncertainty principle motion. So it's a very cold radiation that's left over from the Big Bang. And it's been traveling to us since about 400,000 years after the Big Bang. So the universe started about 13.75 billion years ago. And this radiation was emitted when the universe had cooled down a little bit, when it was 400,000 years old. And it's been traveling in a straight line for almost 13.75 billion years. So the next thing you might be interested in is the temperature difference between the red hot spots and the blue cold spots. And on an average sense, that temperature difference is about 30 microkelvin, 30 millionth of a Kelvin. So the temperature difference is 30 millionth of a Kelvin, and the average temperature is 3 Kelvin. So the ratio of the temperature difference to the average temperature is about 10 to the minus 5. So this thing is uniform to 1 part in 10 to the minus 5, or 1 part in 0.001%. Across the sky. The temperature difference does not vary. The delta T over T is the same to about 0.001% on scales of a few thousand megaparsecs. And so it's very, very isotropic compared to this, where you can see huge differences between clusters and voids. And so these are two very, very important facts about reality, that locally in our neighborhood on scales of tens of millions of light years, that the distribution, tens of millions are smaller, the distribution of light and matter is bumpy in space. But when you get out to 50 or 100 million light years and larger, the distribution becomes much more isotropic, and the larger scales you look at, the more uniform it becomes. So I'm not going to talk more about these, but if you want to understand how physicists try to explain these facts, you can search for the inflation model of the very early universe on your favorite search engine. And you have to be a little bit careful what you read on the web, because there's a lot of nonsense there. But if you go to Wikipedia or Discover or Scientific American or Physics Today, then you can find pretty reliable articles. And inflation hasn't been established, but all its predictions are so far consistent with the measurements. So I want to move on to another fact that's even more difficult to appreciate, and that's that the universe expands. And it's useful to think about why we think the universe expands. So if we are saying that the universe expands, that must imply that we have measuring devices that are not expanding in exactly the same way. Because if our measuring devices expanded in exactly the same way, we'd never see the expansion of the universe. And so it's useful to think about what holds our measuring devices together. So I have this guy, and this is a pretty good measuring device. And on the scale of this object, we only have to worry about two forces. So one's gravity. So if you have a mass, and maybe I can. Do you have like a keychain or something, or a key or something? Can I drop this?
Yeah.
Okay, so I have this has a mass, and the Earth has a mass, and there's a gravitational attraction between them, and you know what that law is, it's Newton's inverse square law. So the force between them is proportional to the product of their masses times Newton's big G, gravitational constant. And it's inversely proportional to the distance squared. So if you double the distance, then you have a r squared in the denominator, so it becomes 2r squared, and so there's a factor of 4 in the denominator now, and so the force is 4 times weaker. If you triple it, it's 3 squared, 9 times weaker. So it's attractive, and you know that if I drop this, it gets pulled down, and the Earth gets pulled up. Thank you. And that's an attractive force. And there's also the same sort of law called Coulomb's law for the electric force, except in the electric case, you have two kinds of charges. You have negative charges, and an example of that is the electron, and you have positive charges, and an example of that is the proton. So if you bring two electrons together, they get repelled, and if you bring two protons together, they also get repelled, but if you bring an electron and proton together, they get attracted. And that's Coulomb's law. So like charges get repelled, unlike charges are attracted. For Newton's law of gravity, it's always attractive. So these guys are both inverse square laws, so we can easily do a computation. You just take two protons and bring them close together, and Coulomb's going to push them apart while Newton's going to pull them together. So have any of you calculated the ratio of the electric repulsion to the Coulomb attraction, to the gravitational attraction? Has anybody calculated that? Is the repulsion much weaker than the gravitational attraction? Does anybody think it's weaker? Who thinks the electric repulsion is weaker than the gravitational attraction? Can you put your hands up? Who thinks the gravitational attraction is weaker than the electric repulsion? Okay, so half of, well, 1/3 of you put your hands up. So 2/3 of you didn't answer. So you're just really shy, or? Okay, well, so the electric repulsion is much stronger. It's 36 powers of 10 stronger than the gravitational attraction. So you're sitting next to somebody, or pretty close to somebody. Are you repulsing your neighbor gravitationally? Who thinks you're repulsing your neighbor gravitationally? Are you attracting your neighbor gravitationally? If you think you're attracting your neighbor, can you put your hands up? Okay, so that's the right thing. What about electrically? Are you pulling your neighbor to you with electric force? Because you're a bunch of charged particles, right? You have electrons and protons. Are you pulling your neighbor electrically? Can you put your hands up if you think you're pulling your neighbor to you electrically? Are you pushing your neighbor away? So one hand. Are you pushing your neighbor away electrically? One hand. Okay, so the rest of you don't have an opinion, or no effect electrically. So there's no effect because you're made up of molecules, but we can think about this in terms of atoms. So atoms have this electron cloud, and they have a certain number of electrons, and they have an equal number of protons in the nucleus. So your electrons will be pushing your friend's electrons away, but they're also pulling your friend's protons to you. And so Coulomb's law just depends on the charges, and so those two forces cancel. So that's because bulk matter is electrically neutral. So as you get to larger and larger scales, everything becomes electrically neutral, and the electric force is no longer important. But the gravitational force is always there. And as you go to larger and larger scales, if you scaled up your masses to the scales of planetary masses, you'd pull each other much strongly than you would if we just had your regular masses through the gravitational field. So large scales is completely dominated by gravity. Well, at small scales, electric force completely dominates. So it's made up of atoms. So atoms have electrons, clouds, and those electrons don't like each other. So they try to move away, but they can't go anywhere because there's electrons and the other atoms around them, and that prevents these guys moving. So this guy is very rigid, and it's held together by a much stronger force than gravity. But as you get out to the size of the solar system and you get out to the size of galaxies, gravity is the dominant force. And so if you want to talk about cosmology, which is the stuff on very large scales, you have to use the most accurate model we have for gravity. So the first model that was reasonably accurate was Newton's model in the early mid-1600s, and he came up with this inverse square law. And the way he did this is he kind of set up a system of laws such that you had a fixed space and a uniform time. And he let his apple fall, and he measured this uniform time with his pendulum, and space and time did not deform. And he got this inverse square law of gravity. Then in the early 1900s, starting around 1905 and going on for maybe 10 or 11 or 12 years, Einstein realized that he could improve on Newton's description of reality by allowing space and time to deform in response to that falling apple. And so he found that there'd be corrections to Newton's picture of reality. And these corrections became really important when things were moving at speeds close to the speed of light, or they were in very strong gravitational fields, or they were on very, very large scale distances that we're looking at. And his model of reality is called relativity, and its final version is the general theory of relativity. And it's, in some sense, the collection of nonlinear coupled partial differential equations. And we can't actually go out to those length scales or those speeds and actually get any intuition. So the only way you build up intuition of what's happening with general relativity is you solve the mathematical equations, and then you make predictions for what people should see in the experiments using telescopes or whatever experiments they're doing. And if they agree, then you're happy with general relativity, and you say that it describes reality. And I'm not going to sit here and solve those differential equations for you because we don't have enough time. But what I'm going to do is I'm going to solve those equations. I've already solved them. And I'm going to translate those solutions into English, which is a very inexact translation. And so you've got to remember that. And so what general relativity does in the context of cosmology is that it wanders around in space, and where it finds underdense regions where there's less matter on average, it creates more space there. And that space has to go somewhere because the old space doesn't like that space to be hanging around. And so that space spreads out, and everything lives in space. So as the space is spreading out, it takes it along for the ride. And I've got some demonstrations of what happens. So I'm going to start with the one-dimensional space. So we live in a three-dimensional space. You can see there's two horizontal axes here and one vertical axis. So if I want to tell you where my finger is, I need to set up an origin, and maybe I'll choose that corner. And I'll measure the distance from this wall to my finger, from this wall to my finger, and that wall to the finger. And so I have to give you three numbers. But I'm going to do this with a one-dimensional space here first. And so I'm going to ask you to ignore this width. I just put this width here so I can draw waves on this, but all I'm interested in is this dimension over here. And so if I set up my origin over here, I can go with my measuring device and measure the distance to this point, and all I have to give you is one number with some units, and you know where you are. So I've got a measuring device here, and I've got a space. And I'm going to let the space expand. But before I let it expand, I can show you this wave, and this wave has peaks and troughs. And so I can take this measuring device and I can measure the wavelength, and I can do that experiment. And if I let this universe expand, you can see that immediately that the wavelength is getting bigger and bigger as it expands. And as it contracts, the wavelength gets smaller and smaller. So in physics, long wavelength light is red and short wavelength light is blue. So if we start out with blue light and let it expand, it will eventually turn into red light. And your measuring device is held together by a much stronger force, by the electric force, and it's not affected by the expansion of space. So you've noticed this phenomenon in everyday life. If you've ever had a police car or an ambulance or a fire engine go past you with its siren on, and it's a Doppler effect. As that thing is coming towards you, the pitch goes up or the frequency goes up, and as it passes you, the pitch goes down and the frequency goes down. And because the pitch and frequency are inversely proportional to the wavelength, as it's coming towards you, the wavelength is shortened. As it goes past you, the wavelength gets bigger. So it's said to be blue shifted as it's approaching you and red shifted as it's going away from you. And you can see this blue shifting and red shifting here. This is a different Doppler effect. So this is the red shifting. It gets larger and larger. The wavelength gets larger and larger. And we can move on to this. So this is a picture of what I just showed you. So I have a stretchable band here, but there's a couple of things. So it's not just in one dimension, it's in three dimensions because it's isotropic, it's going to be the same in all directions. And it's not that general relativity goes to the edges of space and starts pulling. What general relativity does is it goes into space, creates new space, and that pushes things out. And the simplest model of the universe that fits all the measurements or most of the measurements, there are no edges. So space goes out to infinity. So this is a little bit more technical here. So this is the universe, sorry, this is the universe at an earlier time, and the rubber band is shorter, and this is it at a later time. And you've got to think of this rubber band going out to infinity. And so you have a wave here with some initial wavelength lambda naught, and as time goes on to the present universe, lambda gets bigger, the wavelength gets bigger, so it's getting redshifted. And the size of the universe gets bigger, the distance, the local distance between the hands gets bigger. And so we need to be able to compare the size of the universe at different times. And very loosely, that's what cosmologists call the scale factor, and the symbol for that is A, and it's a function of time. This is when the universe is younger, and as time gets bigger and bigger, it gets to the older universe. The wavelength gets bigger, and the distance between the hands and the scale factor gets bigger and bigger. And astronomers prefer not to use the scale factor. Instead, they use something that they call the redshift. And the symbol for that is Z. And it's defined this way as 1 plus Z is the scale factor now divided by the scale factor at the time at which you emitted the light. So if you emit the light right now, then A of t would be A of now, and A of now divided by A of now would be 1, and that would cancel this, and Z would be 0. So redshift Z is 0 here, but if you emit the light earlier on, the scale factor is smaller, the hands are closer together, so this would be smaller than A of now, and this would be a number bigger than 1, so Z would have to be bigger than 0. So as you go back in time, Z gets bigger and bigger. So redshifting gets bigger and bigger as you go into the past. And the scale factor gets bigger this way, wavelength gets bigger this way, the universe gets bigger this way, time gets bigger this way. So the guy who first saw this redshifting was Slipher, and he was working at the Lowell Observatory in Flagstaff in Arizona, which is about 50 miles south of Grand Canyon. So if any of you been to Grand Canyon, you've probably gone near this observatory. That's the telescope he used. And he collected light from external galaxies outside the Milky Way, put it through a diffraction grating, looked at the spectrum of the light and the ratios of the wavelengths, and he could identify the elements that created that light. And then he compared those elements' wavelengths in the laboratory to the wavelengths he was measuring. And he found in most cases that the wavelengths he was measuring were redshifted. And the next, okay, so this is one thing we can talk about. So Slipher is seeing things moving away from him because of the redshifting. And so naturally people kind of think of this as an explosion, like a big firecracker that sent things out in all directions. And that's not what's happening. It wasn't a huge firecracker a few billion years ago, and Slipher just ended up there in that region of space in 1912, and he's seeing the remains of that. So what actually happened at the beginning of the Big Bang was that things started moving away from each other. And so we want to talk a little bit about whether everything's expanding. We know this is not expanding. And we know we're not expanding. We know the Earth is not expanding. And even galaxies after they formed are not expanding. They're like the ping pong balls on here. What's expanding is the space between the galaxies, but the Milky Way doesn't change in size. And what we're seeing in this expansion is more interesting than a big firecracker. So Slipher wasn't at the center of the universe. There is no center of the universe, and you can see that pretty easily if you think about what's going on here. So we're going to look at a little piece of a three-dimensional space. So there's one dimensional here, one dimension here, and we're going to focus on this piece. And we can see immediately that it just has to be a tiny piece, because if it wasn't, you could go to the edge and look out, and outside would look different than inside, and it wouldn't be isotropic. So if you want to make this flat space isotropic, you send it out to infinity in all three dimensions. And the chocolate chips are the galaxies, so we'll put observers on each one. And we'll also observe in galaxy 2 what she sees. And she'll tell you as the yeast is rising or as the universe is expanding, that she sees every other chocolate chip move away from her. And that doesn't mean she's at the center of the universe, because we can go and ask an observer in galaxy 5 what he sees. And he'll tell you he sees exactly the same thing as the observer on galaxy 2 sees. He sees every galaxy moving away from him also. That's actually what's happening. It's not that Slipher was at the center of the universe and things were moving away from him. But at some time in the past, every point in space started moving away from every other point, and that's the Big Bang. And a few years later, Hubble, who had access to a bigger telescope on Mount Wilson, just north of Los Angeles, was able to collect light from stars in these galaxies that Slipher was looking at. And he found the pulsating stars. I found very famous ones that are called Cepheid variable stars, and probably the most famous Cepheid variable star is Polaris, the North Pole star. And these stars are very useful because of a discovery made by Henrietta Leavitt, I think it was in 1907 or so, where she realized that the pulsation period of the star is very, very regular. And if you can measure the pulsation period, you can get the wattage of the star. And that's called Leavitt's law, the period luminosity law. So once you know the intrinsic power or the wattage of the star, you can just use the inverse square law and get the distance to that star. And that's what Hubble did, because he found these pulsating stars and he used Henrietta Leavitt's period luminosity relation. And he got the wattage, and from the wattage he got the distance. And the distances are here, and V is Slipher's speed that he could measure using Doppler's formula. And so you get the Hubble law here, that the recession speed is proportional to the distance the galaxy is from us. The galaxy twice as far away is moving twice as fast. The galaxy 3 times as far away is moving 3 times as fast. And here's a very famous demonstration of Hubble's law. This is from one of the key projects on the Hubble Space Telescope. This is the reason, one of the reasons the Hubble Space Telescope was built. And it was built to measure the Hubble law more accurately. And that key project was led by Wendy Friedman. And this is from their paper in 2001. And you can see on this axis the recession velocities of the galaxies, and this axis the distances. So you can just ignore this, and the distances are the same as these tick marks up here. So a galaxy 100 megaparsecs away from us is moving away at about 7,000 kilometers a second. The galaxy 200 megaparsecs away from us is moving away at about 14,000 kilometers a second. And this straight line is Hubble's law. The recession speed is proportional to the distance. So we have an expanding universe, and I'll just go through this fast because I think I'm running out of time, right? 5 minutes, okay. So we have an expanding universe, and I'm to show you a demonstration of that here, and then I'll talk more about this slide. So I think we can just set it up this way. Sure. Look what's here. Yeah. Okay. That's good. And I just press this or just press, yeah. Okay, so we're in a. I'll come there. Thank you. So we're in a 2-dimensional space here. You have to think of yourself as an ant, and all you can do is walk on the surface of this. And you can't go inside, you can't come out. And this is getting air pumped into it, it's getting bigger and bigger. And these little red pieces of paper are my galaxies, they don't expand with expansion. But if you think about what's happening as you're sitting on this galaxy and looking at this galaxy with a telescope, the light is traveling. If it starts out blue, it travels to you. And it takes some time because the speed of light is finite for that light to reach you, and more space is being created. So that blue thing might get a little tinge of purple. But if you go to a further away galaxy, it takes longer for that light to reach you, and it'll get a little more red. And the further away, it'll be a little more red, and the further away one, it'll be more red, and eventually it'll be very red. The galaxies, if they're all the same color intrinsically, then the further away ones will be red, and the nearby ones will be bluer. And it doesn't matter which galaxy you're on, no matter which galaxy you're on, you always see the same thing. And as you move around over here, there is no center. Every galaxy is an equally good place for an observer to live, and it's isotropic. So the only difference between ants is that they're rich ants that can buy rockets and they can travel on the surface. And the poor ants that just sit on these galaxies, they don't have the money to buy rockets. So the poor ants will actually see everything isotropic on large scales, but the rich ants won't. And those are the guys that are going to see a Doppler effect. The front and the back are going to look different, the sides are going to look different. And so we have special observers in these expanding universes, and those are the observers that are at rest with respect to the expansion. And those are these guys that are called cosmological observers. And so if we say that any galaxy is an equally good place for a cosmological observer to live, then that cosmological observer in that galaxy is going to see an isotropic distribution. So if you go from the Milky Way where I am right now and walk over to the Andromeda galaxy and look around and see it's isotropic, there's a theorem in geometry that tells you if it's isotropic about 2 points, that it's actually homogeneous in space. And that's a much, much bigger symmetry. So an example of a homogeneous symmetry is you take a big jug of milk and you put on your diving equipment and you go into it and you swim around. And no matter where you are, as long as you're not at the edges of the container of milk, it's going to look exactly the same whiteness if it's homogenized milk. And that's a homogeneous distribution. It has much more symmetry. And that restricts the spatial geometries we can have. So we talked about the closed geometry. So these are 3-dimensional, but I've shown you 2-dimensional. So there's the closed one, there's the flat one, the top of the surface, and it's going to go out to infinity, because if it didn't, you can go to the edge and look out, it will look different than in. And then there's the open one. And these are, again, 2-dimensional analogs. I can't show you the 3-dimensional one. We talked about the closed one and the flat one, it's going to go to infinity. And then you have the open one that also has to go to infinity. It's saddle shaped. And so we want to do some kind of dynamical model for cosmology. And the easy way to think about this is to think about the radius of this sphere. And as it gets bigger and bigger, the radius gets bigger and bigger. And we can loosely think of that radius as the scale factor. And that's the dynamical variable for cosmology. And Einstein's general relativity gives you an equation for this dynamical variable. And it tells you that as there's a mass there, it creates a gravitational field, and that field creates space, and it moves things around. And so we know that the scale factor is getting bigger and bigger because everything's redshifted. So I'm going to write down symbols that have a dot on top of them, and that's just the rate of change of the scale factor. So A dot is how fast the scale factor changes with time. And that's also sometimes this ratio is called the Hubble parameter. So we know everything is moving away from us. So A dot is the speed of the scale factor. So it's away from us and it's positive. It's moving away from us if we think of ourselves as the origin. So the next thing we might be interested in is whether this thing is increasing or decreasing with time. If you think of this as a car, if you start out and drive away from some point, you turn the car on and you press the accelerator, it'll start moving forward. And that's telling you it's moving away. It has a positive A dot. And the next thing that you might be interested in is whether you continue pressing that accelerator. And if you continue pressing that accelerator, A dot will get bigger and bigger and bigger, and it's accelerating. But if you stop pressing the accelerator and hit the brake pedal, then A dot will start getting smaller and smaller, but it'll still keep moving away from you. It moves away and it slows down and slows down and slows down. And that's the thing we might be interested in next. And there's an equation here, and I'll explain this equation in a little more detail in the next minute or two, but it's very, very similar to Newton's second law, which is acceleration is equal to force divided by mass. And acceleration here is 2 dots on top of A. It's just very unfortunate conventions that in Newtonian mechanics, acceleration is A, and in general relativity and cosmology, the scale factor is A. But I'm never going to use A as acceleration. When I talk about cosmology, I'll always put 2 dots on top of it. So there's a pretty messy equation here, but I'll try to explain this in a few words. So we're going to just ignore these parts now and just focus on this term and these guys over here. So this is telling you the acceleration is equal to some numbers, there's 4 and pi and 3, which are not important unless you want to do this quantitatively correctly. But there's big G from Newton, and that's from his law for gravity, and that comes over to general relativity. And this is the mass per unit volume. And so I'll explain over here with this balloon. I won't turn it back on, but we want to see how space is being created. And we can't, if we have a flat universe, we can't just use the mass because the total mass is infinite. So the easy way to do that is to kind of look at the local region, the finite region of space, and look at the mass per unit volume and see what kind of gravitational field that produces and whether it has enough strength to create space. So there's 2 effects from gravity. One's the space creation process, and the other is for these nearby galaxies. It's equally valid to think in terms of Newton's inverse square law of gravity, and they're going to want to pull together. And that process is going to stop the space creation process of these galaxies that are very heavy locally. And we know that happens with the Milky Way and Andromeda because they're so close together, they're pulling on each other quite strongly, and they're actually coming towards each other because they're very close together, they're very heavy, and the inverse square law tells us they're going to move together, while the Einstein effect for space creation is more important on larger scales. So that negative sign is just telling us that in terms of Newton's law, if you have mass there, they're going to, and they're close enough, they're going to pull together, and they're going to give you a deceleration. So they're going to slow down the space creation process, and they'll stop the expansion eventually, because Andromeda is going to run into the Milky Way, and we don't have to worry about space creation there. So the next thing we have here is pressure. And pressure, if I use this normal units that you use in introductory physics, there'd be 2 powers of the speed of light in the denominator. I'm using natural units. But if I put the speed of light back there, that tells you this is a relativistic effect. And what the pressure is measuring is the energy of motion, because these galaxies, I wasn't rich enough to give you a completely accurate demonstration, because you can think about what's happening with Andromeda and Milky Way. They're actually moving towards each other. So these galaxies are not stuck on here. They actually move a little bit on the surface. And that kind of demonstration, an analog version of that, is not that easy to make. So because these galaxies are moving, they have energy of motion, they have kinetic energy. And once you have energy, you know from E is equal to mc squared, there's some equivalent mass. And once you have mass, that's going to create a gravitational field. So the energy of motion is responsible for the gravitational field also. And this 3 here is just because there's 3 dimensions in space. So you have motion in 3 possible dimensions, and that's what you call the pressure. And so this is just the active gravitational mass density, active gravitational energy density. It's the source of the gravitational field in general relativity. In Newtonian mechanics, only this guy is important because there's 2 powers of c squared here, and there's a v squared velocity divided by v over c squared. So at low speeds compared to the speed of light, v over c is tiny, and this term is unimportant. But in general relativity, it gives you an even bigger deceleration. So you're really happy and you go and tell your astronomer friends that you predict A double dot is less than 0. And they go and measure A double dot and they come back and tell you that it's actually greater than 0. So you're left with 2 options. One option is to say that that doesn't matter because Einstein was wrong and this equation is incorrect, and so we can throw it away. And we just have to find a new equation to describe what's happening. But we could also be quite conservative and realize that the version of this for black holes works very, very accurately. and it predicts gravitational waves that agree with the measured gravitational waves. It predicts how binary pulsars spin down. It predicts the bumps in the microwave background with fairly good accuracy, to within a factor of 2 or 3. So you might not want to throw away general relativity, and instead you can take advantage of the fact that general relativity doesn't tell you the matter content of the universe, and so you can add some new form of matter there. And that's what we do, is we add in this cosmological constant, which we call lambda, and it also has an energy density and has a pressure, but it has a very strange equation of state. Its pressure is equal to minus its energy density. So rho lambda plus 3p lambda is minus 2 rho lambda. And if you make rho lambda significantly bigger than rho matter, it can overwhelm the positive piece here and make everything inside the square parentheses negative. And that negative sign will cancel that negative sign, and then you'll get accelerated expansion. And that's what dark energy is introduced for. And it would be a very, very silly thing to do if you're just trying to patch together general relativity to explain one measurement. But there's half a dozen different ways of measuring dark energy, and they're all roughly consistent with each other. So adding the substance explains half a dozen different observations. And we also know such substances exist in the lab, and they come from vacuum fluctuations, from Heisenberg's uncertainty principle fluctuations. I'm not going to talk much about that, but I'll just give you some things you can search for on Google. So one is the Casimir effect. And I'll tell you what this is in a second, and the other is the Lamb shift. So quantum mechanics tells us through something called the Heisenberg uncertainty principle that there's a vacuum, and the vacuum is not empty. There's motion in it all the time, and that gives you a whole bunch of effects that you can actually measure. So the Casimir effect is taking two parallel conducting plates and working out what electricity and magnetism do when you have these two conductors really close by. And they change the geometry of space. And when you solve the Schrodinger equation for quantum mechanics, you have to make sure that your electric field vanishes on these conductors. So you don't have as much structure in the electric field when you have these two parallel conducting plates as you have when you have an infinite space, because there's no boundary conditions in that infinite space. And what happens is that these plates feel a force from the 0-point fluctuations, and that's the Casimir effect, and it's measured. And you can describe these things in terms of a fluid that has an equation of state of this form. But we're seeing this on very microscopic scales, not on cosmological scales. And the hope is that there's something like this happening on cosmological scales also, but we haven't seen that yet. So I'd better stop here because I've already run over time. Thank you.
You have time? Do you have time for some questions? Yeah.
So you talked about the ratio between the for AT and A now, right? For calculating the redshift.
Yeah.
So how do you know the AT? Like, how do you know the light being emitted at? How do you calculate that? Like,
How do you calculate AFT?
yeah.
You don't calculate, you can calculate AFT from general relativity, but the thing you measure is the redshift, and the redshift then can give you the ratio of AT to A now. And the absolute value of A now doesn't matter. So all you're interested in the fraction AT is of A now. But you can't, so you measure, what you measure is the redshift, you don't measure the scale factor. And you deduce from the redshift what the scale factor is.
Okay. So generally when we see a light, how do you know like at what points it's like you that can be?
So, so you know, atoms, the way you construct atoms is there's a nucleus and this electron energy levels, right? And so when the electron drops from one energy level to another, it emits light. And it emits light of a specific frequency. Are you kind of familiar with that? Okay, so atoms have many possible transitions, and so they basically emit light at fixed frequencies, so they have a spectrum. So they don't emit a continuous set of colors, but they emit maybe a few lines in blue and a few lines in yellow, a few lines in red. And so you can take the ratios of those wavelengths or the ratios of those frequencies, and those ratios are fixed for each atom or each molecule. So if you collect this light through your spectrograph and you break it down into its spectrum, you can get the ratios, and once you know the ratios, you know what atom emitted it. So you're not looking at the absolute wavelengths or the absolute frequencies, you're looking at the ratios of those wavelengths. And so whether it's emitting the light way back in the past or at the present time, those ratios are going to be the same. So you can identify the atom, and then you can go into the lab and measure the frequencies at which it emits, and then compare those frequencies with the frequencies you're collecting in your telescope. And you'll find that they're redder for galaxies further away. And that's how you know it's through the ratios of the wavelengths.
Thank you.
Mhm.
My name is Raghavendra. Thank you so much. My question is recently there was something that about the universe being inside a black hole. You have any thoughts on that?
I haven't looked at those things a lot. So the people who try to make a correspondence between us being inside the black hole and using the boundary conditions and to try to describe cosmology or that, but I am not an expert in that area, so I probably shouldn't say anything about it.
Thank you.
So why does a galaxy not expand? Like, as per my understanding, dark energy and dark matter is what is causing the universe to expand, right?
Yeah, and even atoms and molecules are also. So the space creation process is a general relativity effect, and it becomes more and more important on larger and larger scales. So on small scales, it's very weak, because on small scales, at least even for this guy, if you're talking about the electric field, that's much stronger and it holds us together. But when you get up to the size of the table, or you get up to the size of the Earth, Newtonian gravity is a very good description of gravity. And from that, you can calculate that the Earth doesn't expand. And even the scale of the Milky Way, Newtonian gravity is a very good description of gravity. And once the galaxy is formed, it doesn't expand. But these galaxies didn't always exist. And so in the past, they were much more diffuse. And as they started getting pulled in, the outer edges were getting pulled out. And so there was some expansion of that part, but that's when they were babies. After they were formed, they were like the ping pong balls and they held together. And what's expanding is the space between the ping pong balls.
So the galaxy is too small compared to the size of.
The effect of expansion, space creation, it's very small. And so there is an effect here, but it's much weaker than the effect of Newtonian gravity.
Thank you for the talk. My question is regarding the Doppler effect. So, microwave might redshift to radio waves, and what might radio waves redshift?
Redshift to longer radio waves. So everything gets redshifted towards the red. And that's why, that's one reason why the James Webb Space Telescope was built, right? It's got very good infrared detectors. And so we can see galaxies that are shining with the same colors as the Milky Way, but they can be much further away. And that light has been shifted into the infrared and the far infrared. And so with James Webb, you should see stuff that's a much higher redshift.
So, a follow-up. So, is there any upper limit on the wavelength of an electromagnetic radiation?
No. You can just keep going. I mean, well, theoretically there is, right? So when you get out to scales at which you can't oscillate, because the universe is expanding. And it's just like a static field effectively. You can't really think of it as as radiation, it's not oscillating. But you can still solve Maxwell's equations. And that thing that gives you oscillating electric and magnetic fields, which is electromagnetic radiation on small scales, isn't doing that on very, very large scales. When the scale is comparable to what's called the Hubble radius, which is thousands of megaparsecs. You don't have those oscillations there, a little bit beyond the Hubble radius, but you still do have some weak oscillations.
Hello, sir. My name is Sharad, and thank you for the lecture. Actually, I have a follow-up question on the last question of the electromagnetic radiation maximum, let's say frequency.
Yeah,
So if you're increasing your frequency to high extent and let's say the energy density
yeah,
keeps on increasing, will that mean it will exceed a particular point where the Planck scale in the space can handle it?
yeah.
It will turn into a black hole?
Yeah, so it was unclear what it would turn into, but if you go the opposite way to shorter and shorter wavelengths, the energy is getting higher and higher. And at some point, you get to energy scales that we don't have equations for. And that's the Planck scale where general relativity and quantum mechanics are equally important. And we don't have a quantum version of general relativity, and things just break down there. That's a very high energy scale. So that's something called 10 to the 19 GeV, where GeV is a billion electron volts. And right now, the highest we go is tens of TeV, which is 10 to the 12. So this is 10 to the 19, 10, so it's 10 to the 28 electron volts instead of 10 to 12, so 16, 17 orders of magnitude higher than we can access in experiments.
Okay. So one more question. Regarding the expansion, we have filaments and voids
Yeah,
in our universe. So given that it's anisotropic in nature, the universe,
yeah.
does that means around the dense regions, the space expansion or is lesser compared to the voids?
So this expands, the picture of the expansion only works in isotropic and homogeneous universe. And so it's only really applicable on scales where you're maybe tens or hundreds of megaparsecs apart. And when you get down closer, you have to account for the anisotropy and it becomes more complicated. So the expansion can be different in different directions. And if the matter content is high enough, it won't expand. So it becomes inhomogeneous and we have much less symmetry and the mathematics becomes much more difficult. But I mean, basically it becomes anisotropic, it's different in different directions.
In the context of simulations like Eagle, Millennium, or in the using lambda serial model,
Yeah.
we do account for this anisotropy time.
So yeah, on very, very large scales, you don't need to do simulations because everything is linear. And you can just do that numerically, solve those differential equations. But when you get down to the scales of clusters, or even hundreds, tens clusters, you have to do numerical simulations. And most of those simulations are not done with general relativity because Newtonian gravity is quite accurate on those scales. And so they build these huge simulations of Newtonian gravity with mass points that are there to be the galaxies. And the fractions of galaxies, and they see them coalesce and form galaxies and clusters of galaxies. Sure.
If people online can post their questions, we'll read it out. Are there any more questions?
Dimension case you talked about, like was an example. So for the 3D case, can we imagine a structure? Look at how this expands.
So for the 3D case, the easy thing is to do the flat case. Well, I guess I didn't put it on the way, sorry. It's this, and you have to imagine it going to infinity in all three dimensions, and that's the expansion in the 3D case. For the flat 3D case, it's Euclidean space. For the closed 3D case, it's too difficult to visualize. I mean, it's a three-dimensional sphere. And I mean, you can think of it that way.
Time to wind up. Let's thank Bharat for a very illuminating talk. Thank you all the audience for your questions and also for turning up and asking.
Thank you very much. Thank you for coming. And if you want longer versions of this, you can find them on YouTube. You can go to Google and put my name in and click on the video tab. We'll go into more detail about dark energy and dark matter.
There's a cards of global warming, the speaker are distributed, so if you haven't gotten one, you can get it from Ranjit at the back or maybe Bhakti at the back. Bhakti, can you speak? So you get collect, so there's some, do you want to say something, say a couple of things?